Welcome back to 6612. Today we're going to talk more about GLMs. So we're going to spend the majority of today's lecture covering exponential family distributions, and there's going to be some derivations associated with that that I'm going to walk through with you. And there, again, are optional readings in the Dobson and Burnett book. So we talked a little bit in the last lecture about generalizing the normal linear model. And this idea of generalized or generalizing comes from the part of GLM in generalized linear models and refers to dropping the normality requirement for the errors, relaxing the homoscedasticity assumption of constant variance, and allowing for some function of the expectation of yi to be linear in the parameters x beta. And what this allows us to do is it allows us to fit linear models to discrete, non-normal, and categorical outcomes. And specifically with GLMs, we focus on outcomes that can be said to have a distribution that comes from the exponential family of distributions. And this is a class of distributions that includes a lot of them that you've already seen, like the normal distribution, the binomial distribution, Poisson, and more. So for a distribution to be said to come from the exponential family of distributions, it has to follow the structure of this equation that's written here. So if you have a random variable y, and this is a PDF here, a probability distribution function, y is said to come from an exponential family if it has parameters theta and phi, and they can be organized such that they are to the exponentiated some function of y, t of y, theta minus some function of theta called b of theta divided by a of phi plus a function of y and phi. And in this form, generally theta is the parameter we're interested in. That parameter is equivalent to mu in the normal distribution, as you'll see in a few slides. And then phi is called the dispersion parameter, which is related to variance. And that's generally speaking a nuisance parameter. And nuisance parameters are parameters that you have to somehow account for in analysis, but they're not really the parameter that you're interested in. And then finally, if you organize your distribution this way and t of y is actually equal to y, then the family is said to be in canonical form. And theta is referred to as the canonical or natural parameter. And again, you'll see an example of that in just a second. So one of the nice things about exponential family distributions is you can use them to fairly easily characterize the expectation and variance of a random variable that follows that distribution. So if y is a random variable that comes from an exponential family distribution, and then you rearrange the distribution to be in this sort of format, then you can pretty easily calculate the expectation and variance for that random variable. For the expectation, you get it. This is actually supposed to be b of theta, indicating that this is some function of theta. You can calculate the expectation by taking b prime of theta, which is the derivative with respect to theta of b of theta, which you can write as d theta of the function b of theta. And then the variance is calculated by taking the second derivative of theta times the function a of phi. So the second derivative we can write b double prime of theta equals d squared b of theta over d theta squared. That just indicates that it's the second derivative. And I'll save that. And then another thing to note about this is the expectation of y for exponential family distributions only depends on theta, and that does not depend on both theta and phi, whereas for the variance of y can be a function of both theta and phi. Though noting that in some cases the variance of the outcome does not depend on the mean at all, like in the normal distribution, though some other distributions do involve dependence between the variance and the mean. Okay, so to try to make that all a little bit more clear, I'm going to show an example of putting the normal distribution into exponential family form. So here we have, say we have a random variable y, which has a normal distribution with mean mu and variance sigma squared. It's going to have this PDF with 1 over sigma times square root of 2 pi, then the exponentiated 1 negative 1/2 sigma squared times y minus mu squared. And so from the previous slide, the PDF of an exponential family distribution can be written, oops, that's not supposed to be a sigma. Let's just erase that. So the PDF of an exponential family distribution is f of y given theta and phi is equal exponentiated function t of y, that's a function of y, times theta over some function of phi, a of phi. And then on the top half here, we actually have minus b of theta plus some function of y and phi, c of y and phi. So we're going to rearrange this normal PDF so it looks like an exponential family PDF like that. So the first thing I'm going to do is take the log exponent of this constant here. So it's a rule of log and exponent that if you take the exponent and the log of something, then it's equal to just the no log or exponent. And so that's going to be e to the log 1 over sigma times the square root of 2 pi times this other exponentiated part that we have over here already. And taking the exponent of that first term is just going to allow us to combine it with that second term so that everything is exponentiated and it looks a little bit more like the exponential family form. So it's a rule of exponents that e to the a times e to the b is equal to e to the a plus e to the a plus b. So I'm going to use that rule here, and I'm going to put these two terms, if you consider that part a and that part b, I'm going to put these two terms together to get e to the and I'm going to move this part to the front because this part is going to be what, and I'm going to move this part to the first half because that's going to be what makes up our sort of function of y and theta. So that's going to be y minus mu squared over negative over 2 sigma squared plus log 1 over sigma square root 2 pi. So, and then that, what I'm going to do next is I'm going to start distributing this, this squared here. Then to get e to the negative y squared minus 2 y mu plus mu squared over 2 sigma squared. I just get that by distributing the square. Minus this function. I'm just going to call this second part right here, I'm going to call that just C of sigma for now, because it doesn't contain mu, our main variable of interest, and then I can replace that C of sigma later, and I don't have to just write it all out again. But okay, so now this is starting to look a little bit more like our exponential family form, where we have this 2 times y and mu, which kind of looks like this t of y theta up here. But, oh, that's interesting, it changes color. But we still have to get rid of some of this extra stuff here, like getting rid of this. Like getting rid of this y squared and this mu squared, which we don't necessarily need for it to be an exponential family form. I'm just playing around with this pencil a little bit and like checking out the colors. I don't know why it's turning like red for that piece but not that other piece, but hopefully it's not too distracting. So then that gives us, I'm going to make that exponent less ugly. That gives us, if we try to make it a little bit more like that exponential family form, we can do we can distribute some of this stuff. We can break up some of this fraction, and we would get positive, because we carry through that negative sign, we get positive y mu, 2y mu over 2 sigma squared. And you get plus, sorry, that's still also a negative. So I'm going to erase that. You get minus mu squared over 2 sigma squared. Then you're going to get minus y squared over 2 sigma squared, and then minus this c of sigma. Okay, so what do we still need to do to get it in exponential family form? I'm going to save this and try to make it another color, so let's see if we can go red again. Okay, what does that do for us? Okay, so this, you can see here, this y and sigma squared doesn't have the mu in it, which is our main variable of interest. That's kind of like this c, and we're okay with, in the exponential family form, we have this term here, c of y and phi, that doesn't contain our main variable of interest, and that just sort of like gets absorbed into the latter part of that exponential family form. So this is going to get pushed over into here. So we don't have to worry about that right now. Then we have y times mu. That looks kind of like this ty theta. So that's good. And we've also got this here, this function of mu squared. And so what we can do is we can now combine these parts and absorb that into there. I'll rewrite out what this sigma squared was. And I think we're going to be in pretty good shape for having this in exponential family form. So I'm just going to do the rest of this on the next page so that there's a little bit more room for you to see what's going on. But we're almost there. So, but going back for a second, so now continuing on, I'm going to make that blue. We still have e to the exponent times, now y times mu minus, well, 2y mu minus 1/2 mu, no, minus, we're going to get there in a second. mu squared over 2 sigma squared minus I'm going to erase that. Y squared over 2 sigma squared plus C of sigma. And then we're just going to want to cancel out this 2. So we can bring this sort of, say, times 1/2 times 1/2. That one's going to cancel, that's going to cancel, and we're just going to have a 1/2 here. And then we're going to get equals e to the y times mu minus 1/2 mu squared over sigma squared minus y squared times 2 sigma squared plus c theta. And we're basically there. So this part I'm going to call, not c theta. Sorry, that's actually supposed to be c sigma. The new c of y and sigma, because it contains the variance parameter but it doesn't contain the mean, and it has it's a function of y. Up here we have your t of y times theta, the main parameter of interest, and then this would be your b of theta, because it's mu squared, it's just a function of mu. And then down here you have a function of sigma, which would be your a of phi. And in this case, so I have that written out on the next slide in LaTeX, so it is a little bit easier to read in case you're having trouble reading in my handwriting. But yeah, so that's the derivation, and it gets you into this form for the exponential family. And now you can sort of identify what each of these parameters would be. So in exponential family form, if we wanted to call it f of y given theta and phi instead of mu and sigma squared, then that would be equal to theta there. This would be equal to, this whole thing would be equal to b of theta. This would be equal to a of phi. And then this whole ugly term out here would be c of y and phi. So that means for us, and yeah, I've written out here a little bit. But as I said, if you have t of y equals y, which is the case here, then this is called in canonical form, which means it has some nice properties that are listed down here that allow you to find the expectation and the variance of your random variable rather quickly. And then you can also calculate, you can figure out what your theta is and what your phi is. So just showing you how you get this mu as the expectation using this property of exponential families that that expectation of y equals b prime of theta. Well, we have b of theta equals 1/2 mu squared, which is equal to 1/2 theta squared. So then the derivative of b of theta with respect to theta is equal to d theta times 1/2 theta squared, which is equal to 2 times theta over 2 equals theta. And that checks out, which is equal to mu. So there's your expectation. Similarly, if we take the second derivative to get the variance, we get b double prime of theta equals d over d theta of b prime of theta. equals d theta of theta equals 1. So in this case, b prime of theta is just 1. So we get variance of y is equal to b prime of theta times a of phi, which is equal to sigma squared, because a of phi is sigma squared. So that works out really nicely. And I encourage you to try this with other distributions like the Poisson distribution. I'm not going to go through the full derivation here for the binomial distribution. However, this works basically the same way, where you can also show that the binomial distribution can be put into exponential family form, where, again, just because I find it easier to see that it's an exponential family form if you actually just write out on top of it what the exponential family form is. I don't know why the highlighter is turned on here. But, so I'm just going to write that out on the top here. So that's, again, that's f of y, and we put it in, parameterize it in terms of theta and phi is equal to e to the t of y times theta minus b of theta over a of phi. And please, if any of these steps don't make sense to you, please post them in the discussion board, and I will spend time writing an answer and also coming up with questions for lab that get at these concepts a little bit deeper. So that's the exponential family form. Here we have the binomial distribution. Here we would say that y comes from a binomial distribution, and typically the parameter for binomial distribution is called p or pi. So first, I just want to talk a little bit about what a binomial random variable means. So if you say y has a binomial distribution, that means that y is the number of times a specific outcome occurs within n trials. So y takes on an integer value that has equal or less than n. Often coin flips are used as an example. So say you have 10 coin flips and you can only see heads or tails, and you see heads 3 times, then your value for y would be 3. Your value for n would be 10. And then your pi here is actually the probability of seeing heads on any particular trial. So that's and so this is the distribution for that sort of coin flip trial probability. And it's used a lot for all sorts of things in biostats as well that we'll get more into later. So if you want to take the binomial distribution, I've said that it's an exponential family distribution, and I just want to show you what it looks like if you put it in that form. So, and I really encourage you to go through the steps of this derivation yourself. I'm not going to do it right now, but I can in class if anybody would like me to. You take this and you take the exponential, you exponentiate it and take the log like you would, and what you end up with is this distribution here. And now you can see the nice pieces of the exponential form where you have y here. So t of y equals y. Theta is equal to log pi over 1 minus pi. A of phi is equal to 1. We just don't have a nuisance parameter for this particular distribution, and that's okay. And then b of theta is this term here. And I'm not going to go through the details here, but I encourage you to drive it on your own and find that if you take b of theta to get the expectation of y, you end up with n times pi, so the number of trials times the probability of success on each trial, and for the variance of y, which is equal to b double prime theta times a of v, which is equal to 1 in this case. So the whole thing is equal to b double prime of theta and times p times 1 minus p. Cool. So why do we care about the exponential family and fitting our distributions into exponential family form? Well, first of all, we want to know if a distribution can fit the exponential family framework, because then we know if we can use it to find things like the expectation and variance. But also we want to know, because exponential families are one of 3 components that underline the generalized linear model framework. And we'll see a little bit more in the next lecture what the other 2 components are and how they fit together with the distributions.